Hello everyone, today's topic is synthesis of thiophene. We will see various methods how we can synthesize thiophene. The first one is ring synthesis, where we take 1,4 dicarbonyl compound, we treated with P2S5 or the reagent which has been shown here. This is also the source of sulfite, and P2S5 is also a source of sulfite. Then by the reaction we get the substituted thiophene. The second one is the Hinsberg synthesis, where from 1,2-dicarbonyl compound and this sulfur compound, by treating with base, we get the substituted thiophene. Here, the base attacks here. If we consider the mechanism, the base abstract the proton from here. We know that this hydrogen is highly acidic as a electron withdrawing group, and also the sulfur is present. Sulfur also can stabilize the negative charge because it has vacant d orbital. So this hydrogen is more acidic. Then when the base abstract the hydrogen from here, a negative charge generates. This negative charge attack the carbonyl. We can see here, attack the carbonyl. Then a negative charge generate an oxygen. Then oxygen, the negative charge on oxygen attack here the carbonyl of ester. This is a Stobbe type of mechanism, as here it is mentioned that this is a Stobbe type of mechanism. Then the negative charge on oxygen attacks here. The double bond moves here, then it moves back. We know OET, the ethoxide, is a very good leaving group. It will leave. Why this type of mechanism is the Stobbe mechanism, where we get a 6-membered cyclic ring as an intermediate. Then the base will abstract this hydrogen. This bond will move here, and this bond will move to the oxygen. Then the oxygen will abstract the proton. It will become the carboxylic acid. Then base will abstract the proton from here. The negative charge will generate here, and it will attack the carbonyl of ketone. Then we will get a 5-membered ring. Then this OH and H, which we will eliminate H water, we will get our substituted thiophene. Here it is mentioned that how can we form the reagent 1,2-dicarbonyl. It can be made by ketone and selenium dioxide. We know that selenium dioxide reacts with the alpha carbon of ketone to give 1,2-dicarbonyl compound, or we can get a 1,2-dicarbonyl compound by benzoin condensation. This is the synthesis of thiophene from 1,3-dicarbonyl compound. This is 1,3-dicarbonyl compound. Base abstract the proton from here because the negative charge on sulfur is more stable. So this is more acidic hydrogen. So base abstract the proton from here. A negative charge generated on sulfur. The negative charge generated on sulfur attack one of the carbonyl group of dicarbonyl compound. Then the bond moves here. A negative charge is generated here. This negative charge abstract a proton to become OH. Then base abstract the proton from here. Negative charge will generate here. The negative charge will attack the carbonyl compound, the carbonyl group of ketone. A cyclic 5-membered cyclic ring will be formed. Then this OH, this H, this OH, this H, which eliminate as water, we will get the substituted thiophene. Fourth one is from cyclohexanone. As we can see, when cyclohexanone is treated with sodium hydride, this is the base H minus. From sodium hydride we will get H minus. H minus will abstract the proton from here because this hydrogen is more acidic. So H minus will abstract the proton from here. a negative charge will generate here. The negative charge will attack. This is the carbonyl. This is the format. This is the structure of this. The negative charge generator here will attack here. Then the bond will go up, then down. OET will leave. We will get this. This aldehyde group will be attached to here. Then when it treated with ethanol and dry HCl, the ethoxide ion from ethanol, the ethoxide ion will abstract a proton from here. Then the bond will move here and this bond will move upward. Then when this bond will move upward, this here, from here will move upward, O minus will be generated. It will abstract the proton at OH. Then OET will attack here and OH will eliminate to give this product. When we react base with this compound, base will abstract the proton from here. A negative charge will generate on sulfur. Then sulfur will do the Michael type addition. As we know, this is a soft nucleophile. So sulfur will do the Michael type addition. This bond will move here and the bond will move here. A negative charge will be generated on oxygen. Then the negative charge generated on oxygen will move downward. Then the bond here will be abstracting a proton to give this compound. Then base will abstract this proton because this proton is acidic in nature. The negative charge generated here will attack the carbonyl compound to give a 5-membered ring. Then OET and H will be removed as ethanol. This OH and here NaH is present. That will be removed as water. Then we will get substituted thiophene. From Wittig reagent. As we know, this is a Wittig salt only because when base will be abstract a proton from here, the negative charge will be generated on sulfur. The negative charge will attack here and the bond will move to this carbon, generating a negative charge. So we will get a Wittig salt kind of thing. As we can see here, negative positive, this is the phosphor violet or the Wittig salt. Then Wittig reaction will be occur because we already have an aldehyde group and here a Wittig reagent is present. Between these two, Wittig reaction will occur and we will be able to get this compound chloranil. When we will be treated this compound with chloranil, we will be getting this thiophene, this 2 substituted thiophene. What is chloranil? This is the structure of chloranil. This is used for the aromatization and can detect free secondary arginine. This is a very famous reagent. This is used for aromatization and this is a turmeric yellow solid. The aspirant of CSRNet and CAD should remember this compound. This is used as an aromatizing agent. Let's see the formation of thiophene through McMurray coupling. This substrate when treated with titanium tetrachloride, zinc, copper coupled and acidic water in the presence of THFS solvent, we get this product. We all know that this is McMurray coupling. This homolytic cleavage occur here and these two coordinated with titanium and the radical generated here, these two coupled to give or to form this bond. Then again when we treated with acidic water, this radical generated here becomes OH and OH. When we treat this compound with pyridine tosyl chloride and then with heat or base, we get this thiophene. How this happen? First, the OH on treating with pyridine and tosyl chloride will become OTS, and OTS, we know OTS and OTS are very good leaving group. Then when we will treat it with base or will heat it, OTS from here, H from here, OTS from here, H from here will leave to give this thiophene. Why H is removing from here, not here? Because if it will remove from here, we will get aromatized product. I have already mentioned in the video that getting an aromatized product is the strongest driving force in organic chemistry. So this is it for today. In the next video, I will be discussing about the aromatic order, basicity order, and reactivity order of our heterocyclic compound, that is spiral, furan, and thiophene. Thank you very much. Do subscribe and like.